Okay, so here's step 4. The depth of water in a tank A in inches is modeled by a differentiable and increasing function h for this interval where t is measured in minutes. Values of h of t for selected values of t are given in the table above. Okay, so here's minutes, and at these minutes, this is the depth of the water in the tank. And height is another name for depth. So something that's important, guys, they're telling you that we've got a differentiable and increasing function. Okay, so increasing just means that it's always each consecutive y value is higher than the previous. But differentiable, you need to know that this means two things. It means continuous and it means smooth. Okay, so no sharp corners. Okay, so use the data in the table to find an approximation for this. Show the computations that lead to your answer indicate units of measure. So this is the derivative at 6. So in other words, this is the instantaneous rate of change at t equals 6. And I have to talk more about approximating a derivative from a table, but basically it goes something like this. So in between here is where 6 lies. So what you could do is you could do the average rate of change on the interval 5 to 7, and that will give you an approximation for the instantaneous rate of change at 6. Okay, so we'll go like this. We'll go h prime of 6 is approximately h of 7 minus h of 5 all over 7 minus 5. All right, so this is the instantaneous rate of change, or you could say the slope of tangent line. There's two ways of looking at it. But then this over here, this is the average rate of change, or average rate of change or slope of secant line. So sometimes you've got to use a secant line to approximate a tangent line's slope. And then this is 18.5 minus 15.5 over 7 minus 5 is 2. This is 3 over 2. And guys, unfortunately, a lot of you got this, but you didn't indicate the units of measure. So I couldn't even give you, this is only 1 point and I couldn't give it to you. Okay, so it's going to be inches per minute. And then right there, this would have been 1 point. And I couldn't give it to you if there wasn't the units. Approximate the value of this integral using a right-Riemann sum with the 4 subintervals indicated by the data in the table. Is this approximation greater than or less than the actual area? Give a reason for your answer. So you should draw a graph. All right, so the x, wait, that's 2. So the x values I'm putting down, and then the y values, and they're all going up because it's an increasing function. 10, 15.5, 18.5, and 20. Okay, so we've got 0 that, 2 that, 5 that, 7 that, and 10 that. Okay, so something like this, and it's got to be smooth. Okay, because that's the differential part. Okay, so the way that a right Riemann sum works, and some of you did a left Riemann sum, and I couldn't give you the points for that, but you had the right idea. So here's the base of the first rectangle. Am I going to use the left end point or the right end point for the height? If I use the left end point, this will be the height and I'll go over. But if I use the right end point, this will be the height and I'll go over. So they want a right Riemann sum, so we're going like that. Okay? And then here's the next base. Go to the right end point. And then there's that. Next base, right end point. And then next base, right end point. Okay. So we're going to have that the integral from 0 to 10 h of t dt is equal to, there's going to be 4 rectangles. So base times height plus base times height plus base times height plus base times height. So for the first rectangle, the base is 2 and the height is 10. For the second rectangle, the base is 3 and the height is 15.5. Right? Yeah. And then the base is 2 again, and the height is 18.5. And then the base is 3 again, and the height is 20. And then you just plug that all into your calculator. Oh, and I guess I'll do approximation signs. But they actually use equal signs. Okay, and then you get here, okay, so you get that this is about, what am I doing? 163.5. Okay, so I'll bring this down. So we get that this is approximately that. Okay, and for that, you get 2 points. Okay, now they're asking us, is the approximation, so this is just an approximation, greater than or less than the actual, the true area under the curve? Give a reason. Well, guys, you could see that it's an over approximation for sure, because all the rectangles are going above the curve. So I'm going to say this. I'll say the right Riemann sum approximation is greater than 0 to 10 h of t dt. But then here's the part where you're going to actually get points, because, guys, always look for vocab at the beginning of the problem. Okay, so at the very beginning of the problem, we were given that this function, always look for vocab at the beginning of the problem about the function. About the function. So they're telling us about the function that it's differentiable and increasing. Well, which of these is the reason, which of these things causes the Riemann sum to be an over approximation? Well, think of a differentiable function. All it has to be is continuous and smooth. So like this is a differentiable function, you know what I mean? And, you know, a right Riemann sum would not always be, all right, so this is a differentiable function. And imagine a right Riemann sum, it wouldn't always over approximate on every interval. So it's not the fact that the function's differentiable that is causing the Riemann sum to be an over approximation, it's that it's increasing, okay? Because h of t is an increasing function. Guys, if you didn't say that, a lot of you gave great arguments about why, but they want you to use the vocabulary, like calculus vocabulary. How much was that? you get just another single point for that, and you wouldn't get it if you didn't say increasing. Okay, now this one. The depth of the water in tank B in inches is modeled by this function here for this time interval where t is measured in minutes. Find the average depth of the water in tank B over that time interval. Is this value greater than or less than, so average depth, okay, than the average depth of the water in tank A over the same interval? Give a reason for your answer. Guys, whenever you see the word average, you can, there's actually two formulas that pertain to this, but this is the formula that will always work no matter what. I just realized this last night. Yeah, on the front of your, like that folder, that red folder that I gave you, on the front it says beware of the word average, and which of these equations are we working with. The integral one will actually always work if you hear the word average. So anyway, oh, my neighbors are making noise, it's distracting me. Okay, so the average, okay, so tank B, oh my gosh. Okay, so for tank B, it's going to be 1 over 10 minus 0 integral from 0 to 10, and then you're going to put g of t in there. So this is 1 over 10 integral from 0 to 10, and then we've got to do this. This has to go in there. But since they've already defined it, you can just go like this, guys, if you want, because we're just going to use Math 9. Okay, so I go to my calculator, and I go, what am I doing? Math 9. Oh, what am I doing? Okay, sorry, I'm so distracted by that tapping. Okay, so 1 divided by 10, and then Math 9, 0 to 10. And then 3.2 plus 17.5. You can't even see what I'm doing. And then sine 0.16 dx. Okay, so it's about, okay, so this is about 6 to, I'll say 4.1. Do we get anything for that? I don't have the thing in front of me, but I'm pretty sure we get a point for that. Let me see. If I still have it. You get, ooh, 2 points for that. Sweet. 1 point for the integral, and then another point for getting the answer. 2. So that's plus 2. But you've got to show this also. And getting that. Okay. Then, but they're asking us to compare this average depth with the average depth in tank A. So for tank A, it's over the same interval. So again, 1 over 10 minus 0 from 0 to 10. But then tank A, all we had to model that depth was this table. But down here, we got an approximation for Yeah, for the area under that curve, which would be the integral, so that's good. So this is, so here we would want h of t dt. Okay, and then, so this is going to be approximately 1 over 10 times 163.5. Okay, and then that is equal to 16.35. Okay, is the value greater than or less than the average of the water intake? It is greater than the average depth in tank A because I guess you could just be like, because 16.6241 is greater than 16.35. I think that's good enough. That's basically what they said. Yeah, really. Okay, so then you get another point. And now finally, according to the model, and you could do this one absolutely. Usually D is like the hardest, but this is so simple you can do it. According to the model given in part C, is the depth of the water in tank B increasing or decreasing at time t equals 6? And I say it's simple, but only simple if you like, you know, are ready for it, I guess. Increasing or decreasing, so this is Susan's table stuff. And you just need to know that the derivative, whether the derivative is positive or negative, is going to tell you that. So, yeah, so it's tank B, right? Yeah, so what we need is G prime of 6. Okay, and I'm going to get my calculator out. So G prime of 6, so I do math 8. Math 8. Okay, and something will come up that looks like that. So it goes d dx, oops, and then you plug the function in. 3.2 plus 17.5. And then this, and then sine x. Okay, and then that. Okay, so this is 0.8871. Okay, so we could say increasing. Increasing G prime of 6 is greater than 0. Okay, guys, so there's that. I'll talk to you later.